Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today as it is every day here in my virtual classroom. Step one aside as we jump into section 11.4 in the Big Ideas Math Integrated Math 2 textbook on volumes of prisms and pyramids. Now everything that we've done from 11.1 to 11.3 I feel is leading up to everything we do from 11.4 to 11.7, or at least the latter half of the section on the volumes and surface areas and things like that, because you need to know how to find areas of things to get those. You need to know how circumference works and all that. It's just all a build up, and those things you might have known in the past from 11.1 to 11.3, or at least in some way. Maybe know things on volumes, and if so, maybe this video is not for you, in which case you can switch off. Otherwise, go and check this one out. We got a solution guide video coming up after the lecture portion. If you want to find timestamps for this, go to the description section down below. You can find all that material there, and you can find a PDF of this as well. So go ahead and check that out. We're going to start with that lecture portion right now. Have a calculator handy if you're going to be following along, because we're definitely going to be doing a lot of rounding. Now we are going to classify solids. That means give them their name, just like how in 2D shapes, polygons, we give square and things like that. We're going to call things what they are, and find volumes of prisms and cylinders. That's the head point. A lot of new core vocabulary. Polyhedron, kind of the polygon of the 3D world. Face, kind of like the side of the 3D world. Edge is the sides that we know. Vertex, like the angle of the 3D world. Volume, like the area of the 3D world. Cavalieri's principle. I have no idea what that is. We'll find out together. And similar solids, kind of like similar polygons, similar lengths and things like that. Similarity. We're going to refer to how things are cubed in that way. Previous things we'd have to know from before. The word solid, basically of the 3D shape. Prism, well, I don't remember when we actually used these, so I'm going to name them out. So solid, prism, pyramid, cylinder, cone, sphere, base, and composite solid. Yeah, I don't know when those things specifically did pop up. Maybe they did, and I'm just totally forgetful. I do apologize on that. Okay, let's classify solids. Hey, a three-dimensional figure or solid is bounded by the flat or curved surfaces that enclose the single region of space. A polyhedron is a solid that's bounded by polygons called faces. Sorry, I was going to go back again one more time. A solid, like a sphere is a solid, but it's not a polyhedron. Just like a circle is a shape, I guess the 2D word is shape, but it's not a polygon because it doesn't have like sides, as spheres don't have edges. So a polyhedron is a solid that's bounded by polygons called faces, so it has polygons. An edge of a polyhedron is a line segment, boom, like that, formed by the intersection of two faces, and a vertex is a point where three or more edges meet. So again, edge is kind of like the side of old, face is like your new kinds of sides that we'd say here, and vertex is like an angle. The plural of polyhedron is polyhedra or polyhedrons. I tend to say the latter, I believe. Okay, so several types of polyhedrons, yes, I would say that, are prisms and pyramids, because you can see all the faces are of polygons. These are generally rectangles, and maybe that's a square base, but with triangles at the top. We'll be classifying these in general, calling them like what makes a pyramid versus a prism. I'm sure they're going to separate those. They didn't mention what a pyramid is just yet. Not polyhedrons. A cylinder is not, a cone is not, a sphere is not. Their connection is they contain something that's not a polygon as a facing. The cylinder has two circular bases. The cone has a circular base. The sphere doesn't technically maybe have any faces, but it's completely circular in nature. So like I said, if circles are not polygons, then that doesn't work. Okay, to name a prism or a pyramid, you use the shape of the base. So I'll read what they say first, and then I'll say things after that. The two bases of a prism are congruent polygons and parallel planes. For example, the bases of a pentagonal prism are pentagons. So you can see on top and on bottom we have pentagons. Those are the unique shapes of these prisms. Therefore, it is a pentagonal prism. Now I'm going to say more about bases with that in general. The base of a pyramid is a polygon. For example, the base of a triangular pyramid is a triangle. So this is the base here as well. Now, some things they do, so they did mention some things, there's some things they did not mention here. And there's also a phrasing I did not see, which I kind of want to get into, but I'm sure they're going to talk about it more with the surface area. Number one, the bases do not have to be on the top and bottom. You could have, and I don't have anything with me right now, but you could have something that it flipped over, flipped on its side. If this pentagon facing was on the front and this was on the back, it's just a flipped over version. That doesn't change the fact it's not a pentagonal prism. So how do you identify the bases? Well, if it's a rectangular prism, anything could technically be called its base. At that point, you might as well call the top and bottom the base. But for a prism, the lateral faces, these ones on the sides, I'm circling around the side ones right here, those would have to be rectangles. In some cases, parallelograms, but you'll see when those appear, when they are, I forget what the name is, oblique prisms or something like that. But otherwise, they're rectangular in nature. You would not have a pentagon in this case because it wouldn't make parallel bases, all that kind of stuff. So these are the unique ones on top and bottom. Now, the triangular pyramid, everything's a triangle, so it's hard to say, but the base would be the unique one outside of it, and then all triangles meet to this apex here afterwards. So I'm sure they're going to say more about them later. So to name some of these ones, name the polyhedron in this case, I would call this one a rectangular prism. They're saying classify whether it's a polyhedron or not. So it is a polyhedron, this is a polyhedron, this is not a polyhedron. As this is a polyhedron, it is a rectangular prism. It has all rectangular faces, including what would be, I guess, the top and bottom as bases. So we'll call it that. That's what they call it. This one here is also a polyhedron, and it is a pyramid. But what kind? This is the unique bottom and base. And most pyramids will be facing upward like that. Some will be upside down. I guess they could be any direction. But that's a hexagon, hexagonal shape. So it's a hexagonal pyramid. And that's what they say here. Last one. A circular pyramid, if you will, and that's something I'll probably be mentioning later, especially when we talk about probably more surface area, but volume actually still applies. It's a cone. It's a cone. It's an inverted cone, but it's also a cone. It has a curved surface, so it's not a polyhedron. Okay. This is a square pyramid. You can see all sides congruent and the right angle. This is, a semi-cylinder. It's a cylinder with a semicircular base there, so therefore it's a semi-cylinder, I suppose, not a polyhedron. Okay, and then this is an example. This is an example of this is not the base. This is not the base. Just because it's a rectangle or just because it's the bottom doesn't make it the base, because now what are you calling this? It's not a pyramid. It doesn't meet at one common point at the top here. The bases are actually here. This triangle and this triangle. They're separated by rectangles. Rectangle here, rectangle in the back, and rectangle in the bottom. They're separated by rectangles, therefore these triangles, the unique ones, are the bases. This is a triangular prism. It's a triangular prism. It's just knocked over. It's like a block of cheese that you just topped over there. So that's the important one to name there. Okay, finding volumes of prisms and cylinders. The volume of a solid is the number of cubic units contained in its interior. So it's like how much you can fill in something. If you're filling something up with liquid or sand, grain, something like that, how much fill there is in cubic units in that way. Volume measured in cubic units such as cubic centimeters, Instead of square feet, like area, we talk about how much you can cover with something, with wrapping paper, with paint, something like that. Those would be square units. These are cubic units. Here's this part. Cavalieri's principle, I'll call him Cavalieri. Cavalieri's principle, named after Bonaventura Cavalieri, states if two solids have the same height and the same cross-sectional area at every level, then they have the same volume. So you can see here are two examples of prisms, and I wish that they named what kind this was. I think it's called an oblique prism. Not quite certain, but you can see here, this may be a rectangular face, if you can understand the 3D-ness of that, whereas this is a parallelogram. Otherwise, they'll generally be rectangles. But as long as they have the same base area and the same height as we get into volume and talk about that, the cross-section being the same, because this cross-section being the same square base area with that same height, then they will occupy the same amount of space. They have the same volume. The way I would equate this, and again, I didn't prepare this, is say you had a stack of paper, and you took that paper, you wedged and held the sides and you bent them over. It doesn't change how much paper you are occupying as an overall just because it's going that way. Excuse me. This is a stack of paper just going that way instead of going straight up. Still equal in volume. Cavalieri must have had a lot of paper in his time to demonstrate that. All right, volume of a prism. Here's the formula, and it's a very basic formula. If you know the volume of a rectangle is base times height, volume of a prism is also base times height. The difference is this B being capitalized, lowercase letters are generally with respect, they generally have to do with one-dimensional units, lengths. So height is a length. This B here is a two-dimensional unit. In this case, V is 3 dimensions. 1 times 2 is 3. One-dimensional unit times two-dimensional unit is 3-dimensional unit. But because it's a two-dimensional, it's a capital B. How come? It's not just base length, it's area of base. So whereas a rectangle is base times height as far as length goes, volume is area of base times height. So it's a very simple formula, and if you equate it to the way that rectangles and parallelograms, because parallelograms have the same thing, it's also base times height. Base times height. That's why both of these ones work the way that you see them, whether it's a prism, even the square prism with rectangular faces, or a square prism, oblique prism with some parallelograms involved, it's still area of base times height. The question at hand is, how do you find the area of its base? And the answer is, it depends on what kind of base it is. And that's where things change. That's why section 11.3 was so important, that we knew how to find the area of a regular pentagon, of a regular octagon, of a kite, of a rhombus, on top of triangles, rectangles, and squares. So, and trapezoids. In fact, here's an example of a trapezoid. So we have to know how to find areas of bases. And that's why naming something by its base is so important, because it's a part of our formula. So example, finding volumes of prisms. So we can see a triangular prism here. There's a right angle, so it's a right triangle that can help us find the area of that base. There's a trapezoidal prism here. So we're going to do area of base times height. I'm generally going to separate my work very organizationally, where you can tell where I'm trying to find capital B, area of base, and identify what the height is. The height, by the way, I haven't really mentioned, it's the distance between your bases. It doesn't always go up and down. The height in this problem would have been this h right here. It's the distance between your bases. And this also would have been the height. And in the pyramid, we'll talk more about those later. But let's find the area of this base here. In a right triangle, now there are two different heights, right? There's the height of the prism and the height of your base. 1/2 base times height in the area of the triangle, so 1/2 3 times 4 is 6 square centimeters. That's the area of your base. The height of the prism is 2 centimeters. So area of base 6 times height 2 is 12. That's 12 cubic centimeters of volume. Part B, area of a trapezoid is you average your bases and multiply by the height. So you have a base length here of 14, another one of 6. Base length meaning in your base. That's the problem, saying base in multiple ways and height in multiple ways. So you average 14 and 6 and you get 10. And then you multiply by the height of the base, which is 3. That's the perpendicular, that's the distance between your bases. And then you get 30 square centimeters as the area of that base. The height of the prism is 5. That's congruent. That's consistent throughout. So area of base 30 times 5 is 150. That's 150 cubic centimeter volume. Okay, let's talk about... Give me 1 second. I forget how I introduced this. No wonder why they're not talking about pyramids, really. I'm sorry if in the very beginning of this section thing, I said volume of prisms and pyramids. I hope I said volume of prisms and cylinders. I don't know if I did anymore, because my mind started getting on pyramids when they started talking about prisms. Excuse me, when they started talking about polyhedrons. Okay, a cylinder, consider a cylinder with height h and base radius r, and a rectangular prism with the same height has a square base with sides of length r times square root of pi. Okay, they're stretching a little bit. Cylinder and prism have the same cross-sectional area, pi r squared, at every level and same height. By Cavalieri's principle, the prism and cylinder have the same volume. So, here's the thing to me. Even though a cylinder is not a prism, I coin it as a circular prism. If you name it by its base, the base is a circle, and it has the same prism properties that will really help when we talk about surface area, when I re-mention circular prism. The other way it also works is for volume. It's still area of base times height. It just is a very specific base. There's only one type, pi r squared. So area of base times height is pi r squared times height. So if you see me write that specifically for cylinder, we should be all good. But if you just need to know area of base times height, you can still work that out. Area of the circle is pi r squared. You can have an oblique cylinder like that one as well, and it still works, but the height is the perpendicular distance. So let's find the volume of each cylinder. For this volume, we're going to do pi r squared for the area of the base. Pi times 9 squared is 81 pi. They rounded it. No, they didn't yet, but 81 pi times the height of 6 gives you 486 pi cubic feet. Rounded looks like they're using 2 decimal places, so let's get ready to do the same when we work on that. This one as well, excuse me, the height is 7. That is the distance between your two congruent bases. Pi times 4 squared is 16 pi, times 7 is 112 pi, rounded to 351.86 cubic centimeters. So I'll let them find volumes of solids for themselves later. Then we'll talk about similar solids. Two solids of the same type with equal ratios of corresponding linear measures, such as height or radii, are called similar solids. So they have to grow in proportion with each other in every which dimension. The ratio of the corresponding linear measures of two similar solids is called the scale factor. Sometimes I call it similarity ratio. So they both kind of mean the same thing. If they have a scale factor of k and they're similar, then the ratio of volumes is k cubed. We've gotten heavy, I've mentioned lately, I think especially in section 11.2, maybe 11.3, that the ratio of areas between two objects would ideally be k squared. That if you double a length of something, a radius or a side or whatever, in two objects that are similar, then their areas, the ratio of areas, you square that, it's quadruple that amount. Well, the volume would be octupled, whatever. You multiply by 8. 2 cubed is 8. So I think we're going to see that in this instance here. Cylinder A and B are similar. Find the volume of cylinder B. Notice that they don't give you enough information to say, well, what's the height? How do I find its volume? You could do certain things. You could use this volume and that radius to find this height. And because this thing doubled in length here, then this would double in length there. That's a little overkill. What you could also do is just compare the 6 to the 3, say that it doubled, and if the length doubled, then the volume got 8 times bigger, 2 cubed, which is 8. So you have a, like a 8-to-1 ratio, as this is also blank to 45 pi, and then you can find that volume as 360 pi. They didn't seem to round that number, I guess because this was already exact, so I can follow along with it. Okay, finding the volume of a composite solid. So here's one of the last bits. A composite solid is basically an irregularly shaped one. Either you're adding or subtracting volumes with each other, depending on the type of shape that it is. You can see a concrete block here that's basically a rectangular prism with rectangular prisms cut out from them. They don't show you the cross-sectional parts that are cut out, but it would be like this idea here when this guy is cut out from inside. And then this guy, let me use my tablet. And then this guy also cut out from inside right there. We got to remove these two volumes. They're probably congruent, but we got to remove these two volumes from the volume of the other guy. The area of the area. Oh, area of base. Okay, they're getting a little whatever. I'm going to do volume separately, but the volume of the large rectangular prism minus 2 times the volume of the two small rectangular prisms. You can do it that way. They seem to multiply by height after the fact, which is fine. Excuse me, the volume's about 0.4 cubic feet. And this one, you got it. Sorry, this is one I'm hiding right there. You got to cut the volume of that square prism out from outside from this triangular prism, and it is a triangular prism. This is a base, and that's a base right there, separated by the rectangles. So they're not talking about every target word thing right here. It looks like pyramids are saved for a different thing. Again, apologies if I said that from the jump. I should be more careful with that. Okay, so here we go. Vocabulary and core concept check. In what type of units is the volume of a solid measured? They are cubic units. Cubic units. So you're going to see where it says like feet cubed, meters cubed, centimeters cubed, cubic feet, cubic meters, cubic centimeters, things like that will happen. Number 2, which solid does not belong with the other 3? Explain your reasoning. We have a few pyramids here, which are all polyhedrons. So if those are all A's to us, with a square base, triangular base, and pentagonal base. This one is a circular pyramid, otherwise known as a cone. That one's going to be different. It's not a polyhedron. Not a polyhedron. It has a curved surface. Or a surface with curved edges, at the very least. Okay, guys, we are going to jump into what looks like 3 through 6 next down below. But before we do... Hold on, I just activated a magnifier on my screen. I don't want to do that. Before we do, I want to remind you to check out timestamps for the kind of problems you're trying to find, and in the description section down below, and also have a calculator ready. I imagine that since we came off of section 11.3 with areas of regular polygons, we might have to do some of the trig and special right triangles with the 1/2, A equals 1/2 apothem times perimeter. I'm sure it'll pop up somewhere. So guys, let's go ahead. Let's get started here. Numbers 3 through 6 match the polyhedron with its name. They have some names down below. So for number 3, what you're looking at there, you're looking at a pyramid. Excuse me, it's a polyhedron. It's a pyramid. These sides are congruent. These sides are congruent. That's a right angle. It's a rectangle at most known. So it's probably a rectangular pyramid. So that's going to be B. So rectangular pyramid. Let me say B at the forefront there. I don't just want people to write the letters. You hear? All right, number 4. These parts will go pretty fast. Number 4, the bases on top. This is a polyhedron. Oh, they're all polyhedrons. The bases on top and bottom are pentagons. This is a prism, congruent, 2 congruent bases. So it should be pentagonal prism, D. Probably a good time to type these out, but I'm not. Number 5. The base, this is not a pyramid. Number 6 is a pyramid. This one's not. This is a prism. This is a prism. The bases are in front and back. Those bases are triangles. They are the unique types, whereas the rectangles are the lateral faces. This is a triangular prism. That is a triangular prism. I have a feeling I'm going to have a couple yawns here. Haven't slept much. Number 6. That is a pyramid. Well, by process of elimination, it's going to be C. But how come? Because it is a pyramid. All triangle faces meet at the top there, and the bottom is a hexagon. So it is a hexagonal pyramid. This is C. Okay. Let's keep moving forward. Let's look at numbers 7 through 10. Tell whether the solid is a polyhedron. If it is, name the polyhedron. So it's just one step more. I'll name every shape for you, whether or not it is a polyhedron. So on number 7, we have another pyramid. It has 1, 2, 3, 4, 5 bases. This will be a, number 1, it is a polyhedron. And it is a pentagonal pyramid. The base, it's named based off its base. All right, number 8, also a polyhedron. Now, it doesn't look like a regular polygon on bottom. Maybe it is, I can't tell, but looks like a hexagon, 6 sides. So this is hexagonal. It is a prism. It's a polyhedron and a hexagonal prism. Number 9. Number 9 is not a polyhedron. You have a couple things involved here, and last time they called this. So maybe I can't really give this an official name for you other than mailbox or whatever I'd call this. It's a composite solid composed of perhaps a cube or a rectangular prism with a semi-cylinder on top of it. So not a polyhedron. So I guess I can't give you an official name because it's a composite solid that kind of just has the appearance of, I don't know. Is that what mailboxes look like? I'm not trying to remember suddenly. So not much I can say there. Number 10 is a polyhedron. However, these are not the bases on bottom and top. Even though they're possibly parallel with each other, because it kind of looks like a trapezoid thing, and I'll talk about that. Even though they're possibly parallel with each other, they are not congruent. They're not congruent. The prism needs to have congruent bases, such as this and this. So the congruent bases are on front and back, the ones that are irregular, that are trapezoids. These trapezoids are separated by this distance here, which you would call a height. This is a trapezoidal prism. It is a polyhedron. And assuming the lines are parallel, not just any old quadrilateral prism, is a trapezoidal prism. So it is super important that you know the name of, the name of it for a couple reasons. Number 1, to know what kind of area you're doing. And number 2, to note where your bases are. Because if you don't know where your bases are, you can't find the area of that base. So it'll be super important. And we're going to find volumes right now. So number 11. On number 11, with that drawing, we are going to... I'll probably get these ones copied and pasted over for the most part, just so we can identify certain things. We're going to find the volume of each prism. We need to answer them in cubic units as well. So on this number 11, identify where the unique bases are. They are the front and back, not the top and bottom. Once again, this is another trapezoidal prism. It is a right trapezoid, given that that's the right angle. So to find the area, so volume is area of base times height. It's probably the only time that I'm going to officially just write that itself. The area of the base is going to be, you average the bases of your trapezoid. In this case, the ones that are parallel to each other. This 1.2 and the 2.3 are going to be averaged. And you multiply that by the height of your trapezoid. That'll be 1.8, the distance between your bases of the trapezoid, of the base. It's weird because there are different things I'm calling bases. There's the base face, and they're the two bases of your base, the trapezoid. There's a height of your base, that's the trapezoid, and there's the height of the prism, which is this 2, which I'm going to talk about next. So base is half of 3.5, which is 1.75, and 1.75 times 1.8, it's probably close to 3.2. Let's see. 1.75 times 1.8, 3.15. So 3.15 square centimeters is the area of your base. The height of your prism is 2 centimeters. That's the distance between your two bases in your prism. I probably feel like with the inner work, I'd want to generally color code that stuff, but I also wouldn't have that formula part on top generally either. So I don't know. It's kind of hit and miss. I'll just leave it. So the overall volume is area of base times height of any prism. So volume is area of base times height, which is 6.3 cubic centimeters. Sorry. 6.3 cubic centimeters. That's number 11. Number 12. 12 seems a little bit easier. Now, there's more than one way to do something like 12 in that because it's a rectangular prism, which ones are the bases? As long as they're opposite each other, they're bases. You can have the front and back. You can have the bottom and top, which is more conventional. I'll probably do that. Or you can do the left and right. Right, these ones. As long as the height is what separates your bases, it won't matter which one you do. Some people say, isn't the volume length times width times height? Yes, because the length times width would be the area of the base times the height. But don't try and be specific and cute with them. If you know them as area of base times height each time, I think you're going to be well off. I'm not going to copy paste this one. The area of the base, I'm going to use the 4 and the 2, the bottom. So 4 times 2 is 8. That's 8 square meters. The height of this one will be 1.5 meters, distancing themselves from each other. So the volume is going to be this area of base times height. And 8 times 1.5 is 12. You get 12 cubic meters. I feel like they should have started off with that one. Just it's a more basic shape, more basic way to identify it, more basic calculation. Instead, they started with the other one. Number 13. This is one of those, I think, I'm going to keep saying I think until I do figure it out. I think it's an oblique polyhedron. In this case, an oblique prism is the name. Just because it's slanted by Cavalieri's principle, we should also note that the volume would still be the same as long as you have the height as the perpendicular distance between your bases. So the area of your base, this is a triangular prism. So the area of the base is 1/2 base times height. And by base, I mean base length of your base edge. So 1/2 of 7 times 10 can apply here because those bases and heights are perpendicular to each other as well. Half of 70 is 35, so 35 square inches for the area of the base. And the height is 5 inches. That's still the distance between your two bases here. So the volume, total volume, is going to be area of base times height. And area of base times height here is 175 cubic inches. And then number 14, same stuff as before. You do have some congruent bases on top and bottom. Let's use those, whereas the height they're declaring should ideally be the 14. They are rectangular bases, so it is a rectangular oblique prism. So the area of the base in this case is 6 times 11, which is 66 square meters. And your height is 14 meters. So the volume in this case is area base times height. In all these cases will be. Area base times height, which is 66 times 14. 924 cubic meters. And that's your first 4 cracked. Polyhedrons. Numbers 15 through 18. Find the volume of the cylinder. They are all cylinders. Volume of a cylinder is also area of base times height. The difference is area of base in this case is always pi r squared. So your radius and your height are the two things we need to know this time to get area base. The radius is 3 feet. The height is 10.2 feet on this first question, number 15. So the area of base given the radius is pi times 3 squared, or 9 pi square feet. We are going to do area of base times height in this case. So 9 pi times 10.2. There's an exact answer somewhere within there, but they've been doing a lot of rounding to the nearest hundredth. So I'm going to do the same thing. So 9 pi times 10.2 is going to give me 288.398. So I'm going to round that up to 288.40 cubic feet. Volume of cylinder on number 15. Number 16. We have a cylinder, but this time with a diameter given, not the radius. So the radius will be half that diameter, 26.8 over 2, which is 13.4 centimeters. The height is 9.8 centimeters. I still have to find area of base, by the way. I keep skipping that. Area of base, pi r squared, 13.4. 13.4 squared is 179.56. Don't forget the pi portion of this still. This is square centimeters. So, area of base, boom. Height, boom. Let's go ahead and round that guy when we get volume. Volume is this times this, 9.8. So let's do that. That number times pi times 9.8. Big number. I want to make sure I got all that. Okay, 5528.22. 5528.22 cubic centimeters. $5,528.22. Number 17 and 18, oblique cylinders. Doesn't change what we do. We have area of base times height once again. So let's just jump straight into that. Volume, in this case, is area of base pi r squared times height. So this is r, this is h. So this one, 25 times 8 is 200. So 200 pi is an exact value. Obviously, we're going to be, rounding this stuff. So it should be 628.31, I think. That's because 3.14 doubled, 314 doubled, things like that. So 200 pi is 628.318, so 0.32. 628.32 cubic feet. And then number 18, you do have to first identify your radius by dividing 12 by 2. Now, notice they show you that 18. Okay, I'm going to copy and paste this one, actually. Notice they show you the 18 as well, but 18 is not the height. 18 is a form of, not maybe the official term, but a form of a slant height. But it's not the height of your prism. It's not the distance between, not the perpendicular distance between your two bases, your circles. That's why they're giving you that 60-degree angle measure as well, though. They need you to come up with what this actual height over here is. If this is 18, by the way, that's 18. So we'll get into that in a moment. Let's start with the radius. Radius is half of 12, which is 6 meters. Now the height is, this is a 30, 60, 90 triangle. This is the hypotenuse of it as 18. Half of that is opposite the 30-degree one, so this is 9 meters. We don't really need that for our calculations, but we do need it for the height. So the height, therefore, is going to be 9 root 3 meters. That's an exact value. In that 30, 60, 90 setup, 1 to 2 to root 3. So height is 9 root 3 meters. So as far as pi r squared times height, that's pi times 6 squared times height. As an exact answer, 36 times 9 is 324, I think. So 324 root 3 times pi, that's cubic meters. But let's check that out. So times square root of 3 and times pi. 1763.01. 1763.01 cubic meters is the volume. Yes, we needed this height, that distance with that radius. Okay. 19 and 20, make a sketch of the solid and find its volume. Round your answer to the nearest hundredth. So number 19, we are going to sketch a prism that has a height of 11.2 centimeters, and an equilateral triangle for a base. Oh, I can do that part. Where each base edge is 8 centimeters. So what I would do is draw the top portion, if you want to call these bases, and I like to kind of slant them off a little bit, otherwise you kind of get something where you can't really see the 3D aspect of it. But I'll get the slant right here, and it is equilateral. I know it's equilateral because I marked everything congruent, you see? You're just seeing it kind of from a rotated angle there. But we also have this downward height like this right here. This is good practice for you to do. And then a dotted line on the back end of this because it's kind of where it goes. And on the bottom, you need that same appearance of what you have on top. So it's a triangular prism. Everything's congruent. All of these lengths are 8 centimeters. The height is 11.2 centimeters. And you need to find the volume. Okay, so what you might want to do here is kind of just redraw that equilateral triangle in a flat way. This is where we start to have to do some of this other kind of work. In an equilateral triangle where all of these are 8, this is one of those, you could do the 1/2 apothem times perimeter if you want to find the central angle. I'm more in tune with equilateral triangles of dividing this here, working off the 30, 60, 90. So this is 4, and this is 4 root 3 inside. That's your height. So your area of your triangle, the area of the base, is 1/2 base 8 times height of 4 root 3, which is 16 root 3 square centimeters. That's the area of the base. With your height being 11.2, the overall volume is going to be area of base times height. So I'll jump straight into the rounding of that, especially with the root 3 involved. Okay, I'm getting 310.38 cubic centimeters. 310.38 cubic centimeters. So find the area of the base. Again, it depends on how you want to go about it. You could do 1/2 apothem times perimeter, then you need the apothem. I kind of found the area of this entire triangle by splitting it up in the 30, 60, 90 way, given that it was equilateral. Either works. Number 20, a pentagonal prism. So this time it seems like we're going to use the 1/2 AP, I think. Pentagonal prism has a height of 9 feet, and each base edge is 3 feet. So there it goes and telling you it's a regular pentagon. So 1, 2, 3, 4, 5. Again, kind of make it off to the side if you want to get something more unique with it. I'll slant that in a little bit to find each edge. I do want you to draw it. So you can do it, kind of like that. Whoopsie. Okay. Now everything's congruent in the pentagonal prism. As far as the, it's a regular pentagon, all congruent. Each of those lengths are 3 feet. And then you have a height of the prism being 9 feet. The height of the prism is 9 feet. So, as the pentagon, redrawn over here, this is where I would get into, we have to find the area of that base. So I need to find the apothem, given that I know, let's see, I don't need radius, but I need central angle. Given that I know that an entire length here is not 8, it's 3. So half of 3 is 1.5 feet. Just remember this feet. I need the apothem here. I do need to find that perimeter as well. It's a pretty easy calculation, but just remind myself of that. So I need the central angle divided by 2. Central angle is 360 over 5, which is 72. Half of that is going to be 36 degrees there. It's bisected. This was from section 11.3. So to find the apothem, we do tangent. We take tangent of 36, and we get 1.5 over A. So A is 1.5 over tangent of 36 degrees. The perimeter is 5 times 3, which is 15. These are all in feet. So the area of our base the base itself is 1/2 apothem times perimeter, 1/2 of 1.5 over tangent of 36 times 15. I don't really want to round that yet because we're going to multiply by height. I guess at this point, I might as well just say, let's multiply this all by height now. So the volume is area of base. So this guy here is area of base times your height, and the height is 9. So 9 is height like that. So if we do this all in one fell swoop, we'll be good. And I hope you're okay with that. Just because of how we'll work that out. Remember, area of base, 1/2 apothem times perimeter for the pentagon, and then the height going there. So let's go and go to the calculator and type all that stuff in. I will be typing in 1/2, so 0.5, times 1.5 over tangent of 36 times 15 times 9. I'm just kind of writing it the way that I had it written there. I believe I'm in degrees, and I have been this whole time. Let's double check. Yep. So this is 139.36 rounded cubic feet. 139.36 feet to cubed. All right, so I'm writing that down. So, once again, this all stems back to what we did in section 11.3 and understanding regular pentagons and how those volumes work. And this one follows that thing. So 1/2 apothem times perimeter, needed the apothem using some form of trig, and we got it. All right, let's go and move to numbers 21 and 22 on error analysis. Describe and correct the error in identifying the solid. Oh, this is good. Okay, cool. Number 21, rectangular pyramid. Incorrect. So this polyhedron, it is a polyhedron, but this polyhedron is not a pyramid. A pyramid would only have one unique base with the other faces as triangles meeting at an apex. This has two congruent bases that are triangles in front and back and rectangular lateral faces separating them as they're parallel. This is a triangular prism. Yes, it is very common for people to mistake that for a pyramid. Just because you have triangles, only two of them, doesn't make it a pyramid. It's the way that it's drawn, though, right? It's because it's toppled over. If it was drawn the way that we drew this one right here, you would call that a prism. You wouldn't call this a pyramid. So this is what that is. It's just faced differently, right? What if I took this shape, this object, right? What if I took this and drew it this way? Is that suddenly not a prism? I don't turn it over and you go, oh my gosh, now it's a pyramid. No, it's still the same shape as it always was. So just kind of, keep that in mind. All right. Number 22. By the way, a rectangular pyramid, I described it, but a rectangular pyramid would have had a rectangular base and then the triangles all meeting up at, say, some top point like that. So this would have been an example of a rectangular pyramid like that. Okay? That's a rectangular pyramid. Okay. Number 22. Error analysis. Describe and correct the error in finding the volume of the cylinder. So they used a different formula here. They said 2 pi r times the height. 2 pi r is the circumference of a circle, which we will be using this for surface area stuff. Make no mistake, it will be used, but that's circumference, not area. So they applied, I'm sure all their math after that is correct, but they applied the circumference of their circular base in the volume formula when it should have been area of base. So, this goes back to if you don't have the formulas at hand, if you don't have them in front of you and such. If you just know that all prisms and cylinders are circular prisms, volume is just area of base times height, you're really good to go to begin with, like then and there. Because then you can say, okay, area base is pi r squared, so pi times 4 squared, and then height, still 3. So now you have that. So 16 pi instead of the 8 pi that they have there, times the 3 gives us instead 48 pi cubic feet. So there's the final, without rounding, because they didn't. All right, 23 to 28, find the missing dimension of the prism or cylinder. We're still using the volume formulas from before, but this time they give us the volume to find something that's missing. So in number 23, we've got to solve for u. Now in this case, volume, this is a rectangular prism. So we're still going to do area of base times height, right? Area of base times height. Now the area of the base is going to be that 7 times 8. We can work that out. Area base is 7 times 8, which is 56 square feet. But the volume is also established. The volume is 560 cubic feet. That's the first thing they give you. So we have to find the height. It says u, but so h equals u. How about that? So volume is going to be, volume 560 is going to be equal to 56 times u. Divide by 56, you get u equals 10. This is the height, this is a length, this is in feet. U is 10 feet. You are 10 feet. Number 24, once again, same kind of thing, rectangular prism. You do have area of the base. So area, let's start with volume because that's written first. Volume is 2,700 cubic yards. The area of the base is length times width, base times height, however you want to call that. That's 180 square yards. The height is this unknown that we're going to call V. When volume is area base times height, we can say 2,700 equals 180 times V. And then you divide by 180, you get V equals, is that 15? I think that's 15. 15 yards. So V being the height, I'm going to double check that. 2,700 divided by 180. It should be 15, I believe. Yes. So 15 yards, the height, the V. Okay, number 25. This is, as we just saw from before, this is not a rectangular pyramid, it's a triangular prism. Because it's named based off the base, we got to find the area of that base, or use the area of the base and find W. W is also a height. And in fact, all these are heights. All of these ones, even number 26. But for this one, number 25, the volume is 80 cubic centimeters. This is a triangular prism, so when we find the area of the base, we'll be doing 1/2 base times height, which is 20 square centimeters. The height of the prism we're trying to find is this unknown W. So volume equals area of base times height. So height is 4 centimeters. Divided by 20. I say height is in W. Number 26 is, again, this isn't like the base is bottom and top. The base is front and back. This is a hexagon, a regular hexagon. It's a hexagonal prism. We have to find the area of this hexagonal prism. And I had a formula. Remember on 11.3, if you watched, probably didn't that far. Farther into the video, we kind of had a generic way of coming up with the formula. I think it was 6x squared root 3. It was something weird. We'll have to just do it on our own. You probably can't really apply that generally in other things by remembering. But yeah, over here, we're going to go ahead and find the area of that base of the hexagon in a second. But the volume is 72.66 cubic inches. The area of the base is going to be 1/2 apothem times perimeter. Apothem we have to find. Perimeter would be 2 times 6, which is 12 inches. So 12. So what is the apothem A of, this will be easy. The 2 inches is divided in half to get 1, and this is a 60-degree central angle from a hexagon, 360 over 6, divided by 2 is 30. This is a 30, 60, 90 triangle, which has a 1 to 2 to root 3 ratio relationship. A is literally root 3. It's 1 times root 3. So square root of 3 goes here. So area of base is 6 root 3 square inches. Your h, height of your prism, is the distance separated by your two hexagons. That is the unknown x. So volume equals area of base times height. So x equals 72.66 over 6 root 3. Unfortunately, it will be irrational, but I'm sure there is a rounding. We're going to round to the nearest hundredth. I'm sure the rounding is going to be intended to be something close to a whole number, given the 0.66, whatever. So we'll see. Let's jump to the calculator and see what the heck it is we got going. We have 72.66 divided by, I'm going to use parentheses for 6 root 3. You can't forget that 6 root 3 means 6 times root 3, and if you write it otherwise without the parentheses, it will not register in the denominator with you. So 6.991. Okay, if we're rounding to the nearest hundredth, I guess I got to put 6.99, but clearly it wanted to say around 7 inches. But I'm going to write 6.99 just because of the way that the rounding went. At least to the nearest hundredth. Darn, I wanted that 7. Number 27, we have 3,000 cubic feet of volume of a cylinder. The radius is 9.3, so the area of the base is pi times 9.3 squared, which is not rounded. I just got to do 9.3 squared here, which is 86.49. Was that the other number before? 86.49? I don't think so. 86.49 pi square feet. And the height of the cylinder is the distance between your circles, which is y, which is the unknown. So volume equals area base times height. 3,000 equals 86.49 pi times y. And this is going to be the same thing as the previous problem. If you use the calculator for this straight up and didn't round early, and I hope you didn't, but didn't even calculate early, make sure pi is in parentheses with this set. So over here, I'm going to do 3,000 divided by parentheses 86.49 pi. And now we're going to get the better answer. 10.98. 10.98 feet is that y value. Number 28, volume. We haven't done composite solids yet, but we also haven't done word problems. We're getting pretty deep into how many problems are there? 44. We were probably not as many proofs in like critical thinking and stuff. I'll probably use the bathroom after this one if it's okay. It doesn't matter to you. I'm just gonna pause. Volume is 1696.5 cubic meters. The radius is the unknown this time. Radius is z, which is interesting because the area of the base is pi times r squared. So pi times z squared. This is the first time that height isn't the one that's not established. Height is established this time. It's 15 meters. So with that in mind, the volume, 1696.5, equals area of base pi z squared times the height 15. I'll put the 15 actually in front. Let me get rid of that little dot. I'm going to put the 15 out in front of that pi times z. So we have two steps to do. We have to divide both sides by 15 pi and then take the square root of both sides. So z is the square root of this. And that's approximately what? Same thing as before. When I type in 15 pi into here, I have to make sure it's in its own set of parentheses. So square root of 1696.5 divided by parentheses 15 pi. And now I get 6, right? That's the clean kind of number I'm looking for. That's a radius length. That is in one-dimensional units. That is meters. So 6.00 meter radius. Okay, let me pause. Be right back. Okay, so we finished 28. Let's move on. Numbers 29 and 30, the solids are similar. Find the volume of solid B. So we don't actually need to find the solid through calculations of the area, you know, all that kind of stuff. It's a pentagon, and no, we don't have to do all that. All we have to do is compare the ratios of corresponding parts. In this case, and I don't know how I want to specifically write it, but let's call it the ratio of volumes. This is what I tend to do. The similarity ratio. The similarity ratio. R sub S. I know they use K. I don't know. I'll just say similarity ratio. It's my own habit. I'm going to compare those two heights. Notice that the prism A is 9 centimeters, and then prism B is 3 centimeters. So the similarity ratio is 3, which is 3 to 1. Let me write 3 over 1. Now, the volume ratio is going to cube 3 over 1, which is 27 over 1. In proportionality, that means prism A's volume is 27 times more than prism B. So I just have to divide 2673 divided by 27. So yeah, whatever 27 over 1 is, 2673 over volume of prism B is. So listen, there's so many ways to write what you do. The bottom line is we're going to be, cross multiply, divide, all that kind of stuff. Volume of prism B is 2673 over 27. No one way to write this stuff out outside of the fact that you have to cube the ratio, the similarity ratio, the scale factor of those ones. And that number, I believe that's 99. Just because it's one away from what 2700 would be. So 2673 divided by 27 is 99. Yeah. So that's 99 cubic centimeters. And that's the volume of that one. A lot of this you could kind of do, like I could have probably done that within like 5 seconds in my head in that same kind of way. Let's see if I can do that for number 30. I don't know if I can. Oh, maybe I can't for this one. I definitely can't with the numbers, but yeah, you know what? I can't for this one. It's not as easy. Number 30, we have 2 cylinders. Once again, I don't need formulas for this stuff outside of how these things compare. So the similarity ratio is going to be, how about this? Let me just say volume ratio straight up. Volume ratio is going to take your similarity ratio from one to the other, like 12 to 15, and we're going to cube that. So, and that reduces, by the way, to 4/5, and it's probably best that you do reduce that, or you could even call it 0.8. But 4/5 cubed is 64 over 125. Now, 0.8 cubed would be 0.524. So 64 over 25 apparently is 0.524. So cylinder A is 52.4% that of cylinder B, all that kind of stuff if you want to say it that way. So this ratio, let's set it in proportion to volume of cylinder A, 4,608 pi cubic inches over volume of cylinder B. So I will multiply this up here. I don't know how much work you need to see algebraically, but the rest is algebra. So multiply this by that, and then multiply both sides by the reciprocal, like that. I'm expecting a clean number here. I'm going to keep pi out of my calculation when it comes to doing this because I want to do it in terms of pi as long as it's a clean number. So 4608 times 125 divided by 64 is an integer. In fact, it's a very nice integer. This is 9,000. So 9,000 pi. I never multiplied by pi in my calculator. So 9,000 pi cubic inches is the volume of B. Cylinder B. All right, 31 to 34 are our composite solids. Let's find their volumes. So in order to do this, we have to add or subtract certain things based on what you're looking at. So sometimes there's kind of a bit of a setup here. What I tend to do in situations like this, and I guess I'll copy and paste probably all of these over, is I'll call them object 1 and object 2, based on what you're doing with it. So you get a good understanding of what we're doing as a general to get the volume of the total. So I'll coin this one object 1 and this one object 2. So the volume of the total, just so you're aware, is we're going to be adding these two volumes up, the volume of object 1 plus the volume of object 2. They're both rectangular prisms. Let's start with volume of object 1 by establishing what we have here. We have a base, if I call the bottom stuff the base, so you have a base edge of 5 and of 3 in this rectangular prism. So the base of volume 1, okay, the base of volume 1 is going to be 5 times 3, the area of the base, I should say, is 15 square feet. And the height of volume 1 is 2 feet. It's very easy to get disorganized in this unless you do something like what I'm doing here. So the volume of item 1, object 1, is area of base times height, which is 30 cubic feet. Let's leave that for a moment. It's not the final answer, but let's leave that there. Item 2. Item 2 has, in fact, it's double everything. I could tell you this answer now is going to be, I think it's going to be 150 cubic feet. Because I think everything's doubled. Oh, the height's not doubled. Never mind. Okay. Base area of 2 is boom, boom, 10 times 6, which is 60 square feet. The height of rectangular prism number 2 is also 2 feet. So the volume of object 2 is area of base times height, which is 120. Oh, it still is. Wait a minute. And I must have done something wrong in my head with all that in mind. I mean, there's nothing wrong that I did calculating-wise, right? 5 times 3, doubled. 10 times 6, doubled. That's weird that it's still 150. I must have done something wrong in my head that I'm not... Oh, I wouldn't have thought 150. I would have thought 270. So even I made a mistake on that. Anyway, the volume of the total is going to be 30 plus 120, which is 150. Maybe if I speak less and trying to sound smart and like trying to whiz bang some stuff, maybe I can actually get some stuff right. Now, here's the thing though. I did mention organization, and I must forewarn you, there's a chance I can get something wrong. One slight miscalculation, one slight misstep in number can screw the entire thing up. So I'm only hoping that this doesn't happen here. In older videos, I'm sure I was rough around the edges and made some mistakes. That's really why laying this out is super duper important. You know, one small misstep can absolutely do that. So hopefully you're following my layout and my plan so that if you get a different answer, even with yours being correct, you can tell me about it in the comments stuff, and you know, you can still get it right so that you're not just copying everything I say. That being said, let's hope I get everything right. So number 32. Now I've gotten so let's call this one 1 and this one 2 because number 1's gonna be more basic. I've gotten so heavy on telling you guys and preaching the fact that, you know, this is a square prism and stuff like that. But if you know a different kind of formula that'll apply more, this is a cube. This is a cube, and yes, it's area of base times height, but if you want to get even a little faster with this one, if you understand the volume of a cube is by cubing all your stuff there, and you get 64 cubic inches, I mean, I'm good with something that you know how to do. I'm just stating don't get too specific on other formulas if you don't know how to get back into the basics of them or that you mistake them. But a cube, area of base, 4 times 4, 16, times height, 4. We do get 64 cubic inches. The volume of the second one's a little tricky because it is area of base times height if it were a whole cylinder, but we have to divide it by 2. So in this case here, you know, the cylinder would have been this whole thing like that, right? And it would have gone down in there and all that. But there's only half of it. So we have to take the area of the cylinder divided by 2. And remember, it's all about the circular base. That means these are the bases. The height is the distance between them. So for volume 2, we need to get the area of the base as diameter is 4 because that's 4. Therefore, the radius is 2. Let me go one step down here. The radius of object 2 is 2 inches. So that base of the cylinder, semi-cylinder, is pi times 2 squared, which is 4 pi square inches. And the height, the separation between those two semicircles, the height of this is this distance here. That is 4 inches. So the volume of your second object is area of base, 4 pi, times height of 4, all divided by 2. 16 over 2 is 8. You're left with 8 pi cubic inches. So we have 64 cubic inches and 8 pi cubic inches. The volume of the total should be the sum of those two. 64 plus 8 pi cubic inches. When rounded, probably somewhere around 90. So 64 plus 8 pi. 89.13. 89.13 cubic inches. Okay. Let's go to number 33. We have basically a toilet paper roll. There's the layer on the rim that, it's a stack of discs. There's a hollow inside. We have to remove the volume of the inside. So it's a subtraction. In this case, the volume of the total, we're going to do some sort of V sub 1 minus V sub 2 if I identify this as my, I guess I got to copy and paste this and call what I'm going to call 1 and 2. But you have to be good at looking into the shape itself to really make sense of that. So when I say this, I'm talking about here's object 1 and the inside is object 2. Perhaps if I make it a little more transparent looking like that, you could dig. All right. So the volume of the first, now they both share the same height. I don't know if that matters for us, for you. The radius of volume 1, just imagine that inside the hollow part's not there. The radius of volume 1, of object 1, is 8 inches. The area of that base is pi times 8 squared, which is 64 pi square inches. And the height of everything, of both of these objects, is 11 inches. I'm going to use that for both items. So the volume of object 1, and what the examples did in the lecture portion is they just found the areas of both of them and subtracted the areas of the bases first and then multiplied by the height after. You may do that. I'd say maybe try not get too tricky with that. I would just be careful. So area of base times height gives you 704 pi cubic inches. There's the volume of the first guy. The second guy, we have a radius of 3 inches, therefore a base area of 3 pi r squared, 9 pi square inches. We know that its height is 11 inches. So the the volume of object 2 is area of base times height, which is 99 pi cubic inches. So the volume of the total, we're going to take 704 pi and subtract 99 pi from there. So volume of total is 704 pi minus 99 pi. Those can clean up because they both share pi in it, so they can combine. That's 605 pi cubic inches as an exact value. When we go ahead and round that, when we go and round that times pi, we get 1900.66. 1900.66 cubic inches as a whole. So removing the roll out of the toilet paper, having a hollow inside, having a hollow interior. And I guess it's up to you. It's up to the book writers, problem makers, to make sure that you understand what that looks like. But that's exactly what we're talking about for that composite solid. Number 34, once again, something is removed here. The tricky part is seeing all these dotted lines. This is the part that's removed here. This dotted line part over here is just part of the backdrop of that oblique rectangular prism that we're looking at. But they're both oblique rectangular prisms, each with the same height of 5. It's still a volume 1 minus volume 2 aspect to this thing. Let's coin them objects 1 and 2 like we did last time. This 34 part is going to get part of the cut and paste job. I'll try to hide that in a moment. Okay, give me a second. Good as new, close enough. Okay, so we have object 1 and inside object 2. Both of them share a height of 5 feet. feet. That's not going to change. That's the perpendicular distance between your bases, whether it's the inside or the outside. Now, the volume 1 minus volume 2 thing will apply. So for volume 1, let's find the area of the base, and then we'll multiply it by the height. Area of base, it's rectangular. Just by nature, I guess we assume it is. So 4 times 2, which is 8 square feet. So the volume of object 1 is area of base times height, which is 40 cubic feet. Area of base 2, that's a square. That's a square prism. They're showing both of these are ones. So 1 squared, so 1 square foot. So the volume of object 2 is area of base times height, which is 5. So we get 5 cubic feet there. The volume of the total, we are going to be taking 40 cubic feet and subtracting 5 cubic feet. We get exactly 35 cubic feet. Assuming no mistakes were made, we should be just good on that one for number 34. Okay? All right, let's move down to modeling with mathematics. I think it's our first word problem thing. How many problems are we doing total? 44. So we have 10 more to go. Saving all the word problems and critical thinking and how do you see it and your friend argues this stuff, all probably for the rest of the way. Modeling with mathematics. The Great Blue Hole is a cylindrical trench located off the coast of Belize. It is approximately 1,000 feet wide and 400 feet deep. About how many gallons of water does the Great Blue Hole contain? 1 cubic foot is equivalent to 7.48 gallons. We're going to save that last part till the very end. Whatever we get in cubic feet, let's multiply it by 7.48. About C's. So the 1,000 feet wide, I mean, what they're talking about here is it looks cylindrical. So the 1,000 feet, I assume, is going to be some form of diameter. So 1,000 feet, which means half of that is 500 feet. If you're okay with me just dividing now, we can go and talk about that. Now, it goes deep as well. It goes 400 feet deep. Probably not drawn to scale there. If that's 500, then 400 is probably looking just like that. It's kind of a smaller cylinder, if you will. I know it's supposed to be blue, but whatever. So 400 feet. We're finding this guy's volume. So the radius, let me do that calculation. Radius is 1,000 over 2, which is 500. And the height is 400. That's the depth. The depth is the height. So volume is area of base times height. I think that's 10. Oh, not 10,000. It's like 10 million. Geez, what is it? It's like 1 million. Let's go to that. I'm going to do the exact before I do the any rounding, because I'm also going to multiply by 7.48. So 500 squared times 400. 1, 2, 3, 4, 5, 6, 7, 8. 100 million. So the volume is 100 million pi. It's weird to say. 100 million pi cubic feet of wawa. I'm keeping the pi in there for a moment. How many gallons? So when you multiply by 7.48, that'll be 748 million gallons. Oh, pi gallons. Yeah, don't forget that pi. So when you multiply by pi times pi, there's no decimal showing up. I don't think there are enough numbers to do it. It's not like it's like, oh, it's a perfect number. No, it will be irrational. But 2, 3, 4, 9, 9, 1. I missed a 1. 2, 2, 3, 4, 9, 9, 11305 gallons. That's 2 billion, 2.3 billion, 2.35 billion gallons of water. It's a lot of water. I want to check the accuracy of that. I'm going to Google that. What's it called? The Great Blue Hole. How many gallons of water are in let's see, they say the ocean, the world, a pool, the Pacific Ocean, the Great Blue Hole. I've never even heard of the Great Blue Hole. They say approximately 2.35 billion gallons. What was this answer? Yeah, about 2.35 billion. Okay, so they worked it out right. Obviously, they probably got the factual numbers and then kind of worked everything out, but isn't math great? Isn't math great? Okay, number 36. It's like, I'll get the answer. I'm just going to look it up. Number 36, the volume addition postulate states the volume of a solid is the sum of the volumes of all its non-overlapping parts. Agreed. We just did that literally for like problems 31 and 32 or whichever ones. Use this postulate to find the volume of the block of concrete in example 5 by subtracting the volume of each hole from the volume of the large rectangular prism. Which method do you prefer? Explain your reasoning. Okay, so I mentioned this in the lecture portion. Let me pause and get this cylindrical block thing. 1 second. And we're back. Oh my gosh. I had mentioned, just in a previous problem actually, I had mentioned in, I think this problem, that what the book probably would have done was subtracted this circle area minus this circle's area and then multiplied by height, as opposed to find the volume of each of them and then subtract. I already have my preferred version. It's what I did, find the volumes of them and then subtract, just because I have a more tangible understanding of what it is that I'm using. So we're going to do that one though. I forget what their answer was, but we'll just deal. So here we're going to subtract these two volumes. Now the volumes are the same, so once I find one of them, you're all good to go. But there's that one, and hopefully I can kind of copy and paste this and just say here's the other one. So here's that one there. So am I allowed use this postulate to find the volume of the block by subtracting the volume of each hole from the volume of the large? Okay, they should have done the large rectangular. Oh, but they didn't yet because they subtract the area of the bases. So we'll just redo the problem. So I'll call this object 1 and one of these object 2 because you're still going to be doubling whatever that is. So the volume of the total for me, whereas they would have done the area of 1 minus 2 areas of the second times height. I'm going to do the volume of 1 minus 2 of the volumes of the other, which obviously means you have to do the base times height stuff still. So I'm going to be using this one, whereas the book used the other. And I prefer this one. Both are fine. I think the other is really intuitive. I think it's nice to just see that the area of the base. I just feel like there are some things, like what if we cut out pyramids? Right? What if we cut out, different kinds of things where suddenly it's not congruent everywhere? I think that this one is more practical, makes more sense. Anyway, so the area of the base of the first one, it's all rectangular. So the area of base 1 is going to be this 1.31 times 0.66. And they got a number at the time. I don't remember what it is, and I don't know if they saved it till the very end. But that's exactly something. Give me a second, calculator. 1.31 times 0.66. 0.8646. 0.8646 square feet. The answer of this whole thing was really small. It was less than 1, I believe, for the cubic feet even. Yeah, because even the height is going to be... Remember, the height's the same for all of these, by the way. The height is 0.66 feet, so we can use that. That's why they justified in doing what they did. So the volume of object 1 is area of base times height, which is exactly, and this is exact, which is exactly 0.570636 cubic feet. Okay, there's object 1. The second object has an area of base, which is 0.39 times 0.33. So 0.39 times 0.33, which is exactly, this is all exact, 0.1287 square feet. This was the 5, right? So the volume of this is going to be 0.1287 times 0.66, which is exactly 0.084942 cubic feet. 0.084942. Okay, so the volume of the total, we're going to take one of these minus two of those. So volume total is 0.570636 minus 2 times 0.08494. And that's exactly calculator time. 0.570636 minus 2 times 0.08494. It's exactly 0.40072 cubic feet. Now, they should have gotten the same answer from before. Let me go find it and show yous. Let's find that page. They got this one where it says 0.40. So they decided to round in the end, but the 0.40 should be equivalent to what we just said before, this cubic feet, by the way. So yeah, that thing works out and should be equivalent to this one, 0.40, yes. So same answer as we got there. All agrees we are in the right ballpark. So I'm going to write the exact of 0.400752. Just justify that I actually did it all. Where'd you get the other numbers from? I computed it. So I prefer this method. As I can organize my work more clearly for myself. And it can work practically for all kinds of objects, not just same types of prisms. See, this works because, well, sorry, not just same types of polyhedrons. Like I said, if I had two prisms, if I cut out, because we cut out a square prism, if I cut out a triangular prism from there, it would still work. But if I cut a pyramid out from there, or sphere, semi-hemisphere from there, it wouldn't work. And also, if the heights were different, I don't want to be unique and specific to that kind. So I like being how I lay it out here. All right, number 37 in writing. Both of the figures shown are made up of the same number of congruent rectangles. Explain how Cavalieri's principle can be adapted to compare the area of these figures. Well, this is kind of how I explained it. I kind of said it was stacks of paper. I don't know what my official explanation would be in this kind of scenario other than to just state that, they're the same because they have the same height. The base areas are the same. So I guess, yeah, I'll say that. So they're the same. They are the same as they have the same height. And, well, not just area base. What did they call it? Where the cross-sectional area. They have the same height and cross-sectional area. Think of it as stacks of papers. That's kind of where I go with that one. And, yeah. Well, okay, I take it back. We won't call that cross-sectional area. We would just say the rectangles. Okay, because this isn't so much 3D. So I'll say the rectangles have the same length. And the rectangles have the same length. So maybe it's not stacks of papers yet, because this is more two-dimensional in scope when we're looking at that one. So that's what I'd say for that one. Okay, there's number 37 then. Number 38, 38 and 38. Each stack of memo papers, there you go, contains 500 equally sized sheets. Compare the volumes, explain your reasoning. This is where I'm sure I could say the cross-sectional area that I said before. So I'm just going to copy and paste this guy. And this time I'll mention cross-sectional area. So yeah, that's how I see, whoa. That's how I see Cavalieri's principle. They're the same as they have the same height and cross-sectional areas. That's where I'm going with that. That just because you move it around doesn't change how much space it occupies. Where it occupies is different, but yeah, that's what I like about saying that. All right, number 39, open-ended. Sketch 2 rectangular prisms that have volumes. I might need more room. Sketch 2 rectangular prisms that have volumes of 100 cubic inches, but different surface areas. Include dimensions in your sketches. Now, even if you don't know how to calculate surface areas, just basically make sure they're not congruent to each other. Let's do this. Break up 100. I'm going to break up 100 into kind of different factors here. We could do like 20 times 5, and we could do 25 times 4. Well, no, the 5 is still kind of there. I guess there aren't too many ways to break up 100 suddenly. I'm realizing this. 20 times 5 and 10 times 10. As long as the 10 that I break up here can be like 5 times 2, and this 20 is some form of like 5 times 4. At least here, these are the unique dimensions that we can have of these prisms. Rectangular, that's rectangular with this height. So this can be like length, width, and height. And this can be length, width, and height. I believe that these would then have different I'm trying to make sure these would have different surface areas. Even though you don't know how surface area stuff works necessarily. Let me think about this. Oh geez. 10, let's see, 20 plus 140 is 160, and 40 plus 90 is 130. Oh, 80 plus 90 is 170. Okay, at least these will be different. I don't know if that was the most unique way for me to have done it, but that's my breakup of this thing. So they said draw these two. Okay, I'm going to draw one of them here. And this has the height of 5, the length, cubic inches, 5 inches, and 4 inches, and 5 inches. And then this one here has a height of 10, where it has a length of 5 and a width of 2. So this is going to look different, like that. So this is 10 inches and 2 inches and 5 inches. So they were close to having the same surface area, though, when I just kind of calculated them in my head. But yeah, so the volume here, area of base is 5 times 4, which is 20. And the height is 5. So the volume is 20 times 5, which is 100, just like we wanted. This one here has a area of base of 5 times 2, which is 10, and a height of 10. And the volume is 10 times 10, which is 100. And obviously it'll work out because the numbers that I chose were from factors of 10, but that's just growing it. So yeah, they will have different surface areas. That's open-ended, so you can choose what you need to. Probably could have done like square root of 10, things like that, but that's okay. All right, number 40, making an argument. Your friend says the polyhedron shown as a triangular prism, correct? No, triangular pyramid. Your cousin says it's a triangular pyramid. Oh, there it is. Pyramid. Who is correct? Explain your reasoning. Your cousin is correct. Your cousin is correct. There are no parallel, congruent bases opposite rectangular or lateral faces, or parallelogram faces like a prism would have. The triangular lateral faces meet at an apex like a pyramid. Friend is incorrect, cousin is correct. Okay. That was fast. Number 41, making an argument. Wait, was that one making an argument as well? Yes, it was. So number 41, making another argument. A prism and a cylinder. A prism and a cylinder have the same height and different cross-sectional areas. Your friend claims the two solids have the same volume by Cavalieri's principle. Is your friend correct? Explain your reasoning. No. If they have different cross-sectional areas, then it doesn't work. Your friend is not. Your friend is messing up today. Your friend is incorrect. If both prism and cylinder have volume as area base times height, and the heights are the same, but the cross-sectional areas, as in the base areas, are different, then the volumes would be different. Now, if the volumes, now they won't be shaped the same, but if the areas of the bases and cross-sectional areas were the same, you would get the same volume out. That's what Cavalieri's principle was actually bringing up. They have different base areas here, so no. If they had different heights, it's possible. All right, number 42. Cavalieri's principle. This is the first time I've ever heard of the principle, so they're throwing a lot of that at you. Cavalieri's principle states the two solids shown below have the same volume. Do they also have the same surface area? Explain your reasoning. Oh. I'm trying to determine mathematically. First I was trying to figure out logically. I'm trying to ask myself that question now. Maybe. What I'm thinking about is this whole length-width thing. Length, width, height. Now the height is already applied and it's constant there. But now when it comes to length-width, that length and width hasn't changed. That height hasn't changed. But this here is a different number. I think this has more surface area. I'm trying to think practically with paper. I think this has more surface area because I think these sides have more surface area because this now becomes a hypotenuse. You guys don't know too much about surface area yet. So it's kind of interesting that they ask questions when it comes to surface area here. I think these ones are larger now. I think there's more surface to be covered there because that hypotenuse aspect. So surface area is different. The surface area of the oblique prism, solid, has greater surface area on the slanted sides because those heights are now hypotenuses, which are longer than the previous heights displayed. Yeah, whereas the other ones have the same area. This area and this area should be the same because they share the same base length and height. The ones on the right side should be different. This should be larger than that. Interesting. Okay. All right, two more questions. Number 43. A barn is in the shape of a pentagonal prism. Oh, right there. It's not a regular pentagon, though. With the dimensions shown, the volume of the barn is 9,072 cubic feet. Find the dimensions of each half of the roof. Okay, it is a pentagonal prism. That means, therefore, the pentagons are the base and the 36 is the height. So you have options. You can either divide this into a rectangular prism and a triangular prism like that, and then add those two together, or find the area of the pentagonal base, which I think you'd still need to do that kind of thing. You'd have to find the area of the two separate things and multiply by height. So now I'm going back to my previous argument of saying, would I rather find the area of that base on its own and multiply by height, or would I rather find the area of the two different volumes? The two different volumes and add them together. This time I think I'd rather do the base one. I'm kind of more interested in working this out where this is one of the pentagonal bases right here. They're right angles. They have this 18. This is 8. This is some unknown x, which we're trying to find. Oh, I guess we're trying to find it, huh? And the volume's the n total. But this is split up into two different parts. It's not a regular pentagon. I'm not doing 1/2 apothem times perimeter. I take this area, 8 times 18, which is something. 144 square feet. And then I find this one as well. Actually, I think I'd rather do the volume set. I'd rather do the volume set because I know the 9072 is a separation of those two parts. So the only problem is I don't know. It's isosceles there. These are congruent, but they show nothing else about angles. They don't say it's like a 45, 45, 90, unless they say the top is a right angle. Find the dimensions of each half of the roof. Interesting. They don't say that's a right angle. They just show this as isosceles. They don't show any angles there, which totally changes everything. A barn print with the dimensions shown. Okay. I don't know which version I'll do yet. Let's do the one where they're separate. So this is object 2 and object 1. Now there's a volume as this thing sticks back, right? I'm giving it another appearance. So as this sticks back, there's this 36 feet. That's going to be the height. That's your height because it's the distance between your two bases, this base and that back base. So the volume of object 1 is going to be area of base times height, which is 144, 5,184 cubic feet. Now, the volume of the total is the addition of these two, V1 plus V2, plus V2. And we know that V1, and we know the V of the total. The volume of the total is 9,072. So 9,072 equals 5,184 plus V sub 2. So V sub 2 is 9,072 minus that. 3,888 cubic feet. Now, the volume of this is also area of base times height. So 3,888 is area of base times, hold on, my mouse speed just changed, times 36. So therefore, the area of the base of volume 2 is going to be 108 square feet. What I don't know is how in this triangle with these two things as x's, even though if I know this area, 108 square feet, if I know nothing else about it other than its isosceles triangles, how I can determine what x is. I need an angle measure of some sort somewhere. Let me pause and think about if there's something missing. If I know this is a right angle, I'd be good. If I know this is a right angle, then I know this is the square root of 108. It would be 6 root 3. X would be 6 root 3. 6 root 3. Hold on. So 6 root 3 would be 10.39 feet. But I don't know that that's a right angle. So I don't know. So let me pause and see if there's something I'm missing about angle stuff here. Give me a second. Okay, I caught the issue, and it's because I went off my own drawing. I should have gone off my own drawing more. This is 18, so this is 18. So if that's 18, then right here. So that's no known right angle. I'm trying to erase it. There we go. So this is 18 feet down there. Okay, that helps me a lot more. What do I do still? I don't know. So if that's 18, the 108, let me move the 108 out of there. Oh, I guess it's married to it. So basically I need to find this height. I need to find that height and then use some Pythagorean theorem stuff, right? So the area of this base, 108, is 1/2 the base here, 18. I don't know how I didn't see that the first time. Times your height, the height of this. So H is 12 feet. So I have a 12-foot height. And if that's 18, then this is isosceles. Half of that will be 9. And this is 12. Looks like a Pythagorean triple of a 3, 4, 5. So this will be 9, 12, 13, 9, 12, 15. So x squared equals 9 squared plus 12 squared is that setup. We are going to get 15 here. X squared equals 81 plus 144. X squared equals 225. X equals 15 feet. So what do they ask for? Find the dimensions of each half of the roof. It's 15 feet by, was it 36? 36 feet. 15 here, 36 there. So that didn't write. 15 feet by 36 feet. There it is. Okay, fun question. And I think this is the last one here, number 44. A wooden box is in the shape of a regular pentagonal prism. The sides, top, and bottom of the box are 1 centimeter thick. The side, so I see that they're talking about this part. They're saying this part's 1 centimeter, I believe. I don't know about the top bottom that they're talking about. Approximate the volume. Oh, because this part sticks up as well. Okay, I gotcha. Approximate the volume of wood used to construct the box. Round your answer to the nearest tenth. So it's probably hard to tell. I'm going to try and draw. Let me do this. I'm going to pause it and get a higher quality image of this one on my side of the thing. Okay, as it turns out, I couldn't get it super high quality. The image itself is a little blurry still, but because I wanted to separate this stuff and really show you this. What they're referring to for 1 centimeter, there's a distance between these two height-wise. That's 1 centimeter distance. And then, I gotta sneeze. Excuse me. And then this distance, for example, I probably gotta pause again to drink water. This, for example, is also 1 centimeter. So 1 centimeter width there and 1 centimeter height off those things. So when they're talking about the 6 here, that is the top and bottom of the thing, but then it's cut into it. It's cut into it 1 centimeter, and on the sides are cut into it 1 centimeter. So we have a couple things going on here. And yeah, let me pause and take care of this. Okay, still a little congested from the sneeze, but better on the breathing. So we have a couple things going on here, but the basic thing for me is what you see is the 4 centimeters and 6 centimeters. The 4 centimeters is the apothem of what would be a wooden pentagonal prism without any hole stuff cut into it. And the height of the prism would have been 6 centimeters. So finding the volume of that will be a part of what we do. We're then going to cut out pentagonal prisms on top and bottom. They said there's one underneath as well. So we're going to cut out 2 of the same volume, one right here and one on the bottom. And in both of those instances, they have an apothem that's 1 centimeter less than 4, and their height is 1 centimeter. And so we're going to be just using those ones and subtract those 2 things out. That's the idea that I'm seeing here. I'm going to go ahead and go to work on that. Let me just shrink this a little bit. Group it, shrink it, roll it, pat it, mark it with a B. Okay, so I'm going to deal with that object 1, object 2 stuff from before. This is hard to read. This is object 1. And invisible object 2, for all intents and purposes, invisible object 2 is the thing that's going to be cut out. So the volume of the total is going to be volume of object 1 minus 2 volumes of object 2. Give me one more thing I got to take care of. Okay, so for object 1, we need the height. The height of object 1 will be 6 centimeters. That's the easy part. The area of the base is going to be 1/2 apothem times perimeter. So we still got to find the A and the P. So let's do that based off our pentagon. We've done a lot of regular pentagons here in the past, but this has an apothem of 4 centimeters. We just got to find the perimeter by finding out this length here by dealing with the central angle. We've seen it a lot of times. It's 36 degrees, half of 72. 72 is 360 over 5. The sine of 36 is, the tangent. Tangent of 36 is x over our apothem of 4. So x is 4 times tangent of 36. So double x to get a side length, you'd get 8 times 5 is perimeter, that's 40. So 40 times tangent of 36 degrees is that guy. So your volume of base 1 is 1/2 apothem times perimeter. Now I'll leave it exact as long as I can simplify that. Half of 40 is 20 times 4 is 80. So you get 80 times the tangent of 36 degrees. So that is the area of base 1. So as far as a full volume of object 1, we're going to be doing area of base times height. And the height is 6. So 6 doesn't multiply by 36, it multiplies with 80. So volume of object 1 is 480 times tangent of 36 cubic centimeters. I believe that that's all kind of panned out properly for that. That's object 1. Now object 2 is a smaller pentagonal prism with not too much I got to change here. Really, honestly, we just got to make sure that we can follow the same patterns we had before. The difference is this is going to be 1 centimeter less of an apothem, which means it's going to be 3 centimeters. Same 36 degrees and all that kind of stuff. When it comes to this x that's right here, because this is still 36 degrees, the x here, let's call this x1 and x2, X-Men United. x2 is, well, 3 times tangent of 36 degrees. 3 times tangent of 36 degrees. Honestly, I think here I could almost do the like ratio bits. So the perimeter of object 2 is going to be double that and then times 5, 30. 30 times tangent of 36 degrees. I hope that I'm getting my work all sped up properly with that. That should be the perimeter of this. So the area of base 2 is 1/2 apothem times perimeter, which simplifies to 15 times 45 times tangent of 36 degrees. And the height of object 2 is 1 centimeter. So this will also be the volume. The volume of it, because times 1 area of base times height is going to then be volume with that when put together. That's cubic centimeters. So the volume of the total, volume of the total, we're going to be taking, sorry, I'm going to have some spacing out here. This is kind of the last part. We're going to be taking the 480 tangent of 36. 480 times tangent of 36 minus 245 times tangent of 36s, because there's one on the bottom of there as well. So that's 480 minus 90. Notice they both have tangent of 36, so it's like terms. So it's 390 times tangent of 36 degrees in cubic centimeters. With the calculator, we will get 390 times tangent of 36, around 283.35. I'm going to verify that everything kind of works out the way I want it to. I don't always trust my work. It's one of those things. I'll probably pause and check it out, because it's one of those things where one slight thing would have gotten wrong and I go, shoot, I have to change everything. But let me kind of take a look at everything and explore it and make sure that all is how the problem was supposed to be suggested and all of that. But there's my answer for now. Hold on. Okay, looking at the problem more, so I think I calculated everything I wanted correctly, but looking at the problem more, I was asking myself why the box would be constructed this way. If it's a box and it looks like something you can open up and put things in, the box would be filled with wood. So I was asking why the box would be constructed that way, and the answer is it wouldn't. The answer is it would be hollow inside. So I started thinking again that these didn't look the same. This doesn't look like 1 centimeter like that does as well. I don't think this part, I don't think that this part's 1 centimeter. I don't think this counts as a certain height thing. I don't think this is what they meant. When they said it's 1 centimeter thick, just like this part here, I think this whole top is just a whole top. What is the 1 centimeter, I think, is this right here, that it's cut into 1 centimeter on top and bottom, so it's thicker like that. So you're not cutting out from the top and bottom, you're cutting out from the inside, and there's still 1 centimeter on top and bottom. So the one change I need to make is the height of volume 2 is not 1 centimeter, it's 4 centimeters. If there's 1 centimeter removed from top and bottom, then 1 centimeter removed from 6 is 4. So this changes from, well, now I should write what this thing is. Area of base 2 is now this 45, right? But we have to now multiply that by 4 for volume of the second one. So volume of object 2 will be area of base times height. So I think this is supposed to be 180 times tangent of 36. And that's what we remove. We remove the inner volume of that inside guy. And it's hard to kind of draw it unless I have like a chess thing to show you. So I don't remove 2 of something. I just remove that something. So I remove 180, times tangent of 36. And I think that's a different number now, because now it's 300. 300 times tangent of 36. And then we'll get a different value there. Because I was sitting there thinking like, oh, the numbers are good. And then I started looking at the thing and going, wait, what is this object, right? I want to put stuff inside of it. Otherwise, it's literally just a box with nothing to do. And then I was asking myself the whole time, that doesn't look like 1 centimeter with the other thing. And I think it's a photo. So I don't think that would make sense beyond that. So when I calculate this one, 300 times tangent of 36, I'm getting 217.96. So what did they want us to round to? Nearest tenth. So 218.0 cubic centimeters. So that's where I'm going to go with that one. That's what I believe it's supposed to be based on the box nature, the appearance of the thing, and the nature of boxes themselves. We're moving from there. The sides, top, and bottom are 1 centimeter thick. That means the inside is hollow. That's what we're removing. The height of 4. Not 1 and not 2 of those ones. All right, guys. That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. And next will come 11.5, 11.6, 11.7. There's still volumes of things. I think pyramids come next. And then we hit surface areas of them. And then we hit volumes and surface areas as spheres. A lot more to go with a lot of these calculations. One little thing can screw a lot of things up. But hopefully you followed along and it all makes sense. Take care. I'll see you in the next one.